My original video on the Oceangate incident has recently seen an unexpected jump in views. Whether that's because we're approaching the 1 year anniversary, or whether it's because another billionaire has decided he's going to repeat a feat that's been carried out successfully hundreds of times by science and research organisations to prove some kind of point to other billionaires, I'm not sure. Either way, that original video was made when I had 200 subscribers. I expected it to get no more than 1,000 views, and I recorded it over the course of 2 lunch breaks. It was released about an hour before the US Coast Guard announced the wreckage of the Titan was found. The audio quality was absolutely terrible because I had no idea what I was doing. So this is a re-upload with improved audio. I've made no other changes because I prefer to spend my time making videos on topics that I feel better deserve my attention. But for anyone stumbling across the original, I hope you are redirected to this version instead so you can actually hear me. I will interject at a few points to correct some mistakes I originally made. Other than that, there are no changes to the original video. This isn't really the kind of video I created this channel for. It was more for documenting my electronics projects. However, I do quite enjoy discussing current affairs here in the rare cases I feel I have relevant subject knowledge. The only other time I did this was my Ukraine video last year, and that's my most viewed video. This particular story is one where I feel I have some subject knowledge in almost every element of it. So let's quickly go through my credentials. My previous career was as an engineer in the oil and gas industry. The biggest aspect of this was creating and implementing procedures for testing pressure vessels in harsh environments, i.e. oil wells. I also worked closely with ROVs, that's remote operated subsea vehicles, and with saturation divers, and was based on offshore installations for part of the role, and that includes dive support vessels. My last job was working for the British Geological Survey. I was part of a task group for designing a low-cost subsea sampling system. Admittedly, most of this task consisted of me disappointing others by explaining to robotics engineers how expensive the project would be. Interestingly, the design spec for that was for 4 kilometres depth, which is about the depth the Titanic's at. I also worked with data from the 5 Deeps expedition, so I'm surprisingly familiar with DSVs, and that's deep submergence vehicles, of which the Titan was one of them. I also have a fair amount of experience scuba diving, and was involved in an incident which has echoes of the incident discussed here, and we'll get to that later. I think it's very important to establish I'm not a leading expert on any of the elements of this incident, but I have knowledge and experience of most aspects of it. Stockton Rush, the CEO of Oceangate, was not stupid, well, not academically so anyway. He shares some similarities with me. We both have engineering degrees, we both wanted to be pilots at some point, although I went off the idea before I graduated, and we both got into subsea exploration subsequently. I believe we share very little in common personality-wise though. Unlike other videos I've made, I'm not going to be making my usual dark humour jokes and memes and that kind of thing. I think the message here is stark and important enough for that to be left out. I could discuss this incident at length, but I need to maintain some kind of brevity. There are numerous potential contributory factors to this incident. I cannot cover them all, so I aim to cover those that are not necessarily apparently obvious or have been widely misreported on. I'm going to give the benefit of the doubt where possible. For example, when Oceangate state the DSV had 96 hours of life support, I'm assuming they shut 5 individuals in for 96 hours to verify that. My sources are in the description, and any statements about the craft design and operating procedures come directly from Oceangate. To start with, I'd like to briefly describe a project I was involved in when I worked in the offshore industry. Subsea blowout preventers are part of the line of defence to keep hydrocarbons from reaching the surface during drilling of an oil or gas well. They consist of a hefty stack of hydraulically operated valves which can close around the pipe, and as a last resort, a blind shear ram which can cut the pipe and seal the well in. They're expensive, difficult to operate and transport, and rarely even fail at their job. I was part of a group that designed a revolutionary new BOP, that's blowout preventer, that contained a titanium carbide blind shear ram. This was so strong and so well engineered it was capable of cutting drill pipe and sealing the well under absolutely any foreseeable circumstance. As a result, the other rams could be significantly simplified, as in an emergency we knew the blind shear ram would always work. In fact, we were even able to use off-the-shelf hydraulics from commercial construction equipment to operate the upper rams. We decided it was unnecessary to certify this new design as we demonstrated the blind shear ram as incredibly reliable, So the other rams could be considered as non-essential. We could always fall back on the blind shear ram, whatever happened. Okay, so that story was completely made up. I won't do that again, but I'm trying to make a stark point here. Blowout preventers do exist, they are expensive, that's where the truth ends with that story. The fictional low-cost blowout preventer I just described would be incredibly dangerous. What I want to get across here is it can be surprisingly easy to convince someone with little domain knowledge that something is significantly safer than it actually is. Viewers may have seen the CBS video where the reporter reads through the safety disclaimer from Oceangate. We've all signed off on disclaimers like that, it's just paperwork. A passionate CEO and some self-convincing in this case was clearly enough to convince paying customers that this DSV was as safe as you might have perceived my titanium carbide blowout preventers were. And I would like to point out the reporter's not at fault here. Okay, I think that may be the most misleading thing I said in the entire video. Yes, I spend this video essentially discussing how Oceangate presented a false picture of risk. But we could also argue it's the job of a competent journalist to properly investigate and unravel that false picture. Whether it was possible for this journalist to identify and report on the risks is very much an open question. A classic case study for risk miscommunication would be the Challenger shuttle disaster. I won't go into detail here, but the widely quoted figure is that senior management believed the failure rate was about 1 in 10,000, while most of the engineering team believed it was around 1 in 100, which actually turned out to be the true failure rate. One of the many reasons for certification of life-critical systems is to remove the potential for this disparity. We need a third party of experts with no stake in the actual operation. From this point on, we'll discuss technical aspects with which I have personal experience. Stockton stated in an interview that while some aspects may look improvised, the pressure vessel is solid. We'll come back to the first half of that statement later, but I have significant doubts that the pressure vessel was suitable for this application. It's important to appreciate that for atmospheric diving, there's no wiggle room in pressure vessels. They either fail or they do not. There's no such thing as a slow leak in a DSV. This DSV consisted of a carbon fibre composite tube with 2 hemispherical titanium end caps, one of which contained a viewport. There are reports that this viewport was only certified to 1,300 metres of depth, with the DSV regularly diving to 4,000. This particular point is so egregious I'm not going to go into it here. If this actually turns out to be the case, we could almost stop the video right now, no domain knowledge required. But let's just assume that those admittedly pretty credible reports are erroneous. I'd like to talk about carbon fibre composite. Most pressure vessels I've worked with, and most pressure vessels in the world, are metal, usually steel. Steel is correctly referred to as an alloy, not a metal. Metallurgy is not my strong point, as we see in some of my more recent videos. Steel and titanium is ideally homogeneous and isotropic if manufactured correctly. That means it's consistent throughout and has equal strength in all directions. It means if we can adequately test the quality of the material, we can be confident when and how it will fail under pressure. Here's a typical failure curve for steel, though titanium behaves quite similarly. Stress, think of it as force applied, is on this axis, and strain, think of elongation, is on this axis. This section is the elastic deformation regime. If we limit the stress to this section only, the material will recover and not fail. For a metal pressure vessel, we can always ensure we remain in this elastic deformation section by doing the following. We test our pressure vessel to some pressure above the design limit but below this yield point. We physically inspect the material. For metal vessels, ultrasound inspection can reliably detect defects which would cause a premature failure. Monitoring the strain on the vessel using strain gauges or other means. This isn't always necessary, but it's easy and sometimes appropriate considering that the strain in that vessel is proportional to the stress. Crucially, repeated stress cycles can introduce defects, so we must test with the necessary regularity. I do have to admit I'm apprehensive at the concept of a carbon fibre compressive pressure vessel. Carbon fibre composite consists of woven fibres bonded by epoxy. It's very difficult word to say, inhomogeneous, heterogeneous. If there's a sign I quit engineering 6 years before this video to become a data scientist, that's it right there. And therefore much more difficult to inspect. and subject to more numerous failure modes. Oceangate's defence was that they had an acoustic and strain monitoring system in place on the hull. I remain far from convinced here. As we discussed, strain monitoring is of little use if we don't know the ultimate stress of the material. We can only really confidently know that what the ultimate stress is if we know the material is free of significant defects. Stockton stated it's impossible to test for such defects. Now, my knowledge of carbon fibre composite is quite limited for this application, but that statement is untrue. Here is a testing service offered for bikes, and I'm not here to disparage bikes. A front fork failure on a mountain bike could absolutely be fatal. X-ray testing seems to be the gold standard. If no suitable test rig was available, the only viable approach in Oceangate's case would be to commission one. If that was not possible, carbon fibre composite is not an ideal material and we don't use it. I'm not saying a carbon fibre composite DSV is not possible safely, but I'm confident a significant amount of effort is required to ascertain the integrity of such a vessel. I see little evidence that Oceangate made this effort. To understand whether a construction is safe would require extensive knowledge of failure modes, test regimes, and fatigue effects. This would be at least a PhD level of knowledge. This is another reason certification exists. It's not just a catch-all excuse. It ensures a trusted third party with that knowledge has applied it. Perhaps of even more concern to me is the interface between the carbon fibre composite and the titanium end caps. Interfacing different materials is always a challenge. Every other DSV in existence has a pressure vessel consisting of a metal sphere which does have viewports. Oceangate posted this video that shows the titanium sealing rings being installed onto the carbon fibre composite with epoxy resin. As far as I'm aware, this is probably the only viable option to do so, but I'm far from convinced it's suitable for the following reasons. I'm assuming this resin has some suitable level of compliance. Regardless, it's subject to differential strain between the two materials. This is likely to introduce cracks or defects, not necessarily a critical issue if properly identified and managed. But I see no evidence of inspection of this interface, for example by X-rays. Stockton has previously quoted that is impossible. A visual inspection is clearly impossible, and I absolutely would not trust my life to an uninspectable seal. For such a critical installation, I'd expect a dust-free environment, maybe even temperature controlled, with stringent handling procedures and a vacuum degasser for the resin. I see none of that in this video. It was performed in an open warehouse. Stockton has clearly stated his philosophy of, as long as the pressure vessel is secure and we can ascend, we are safe. Both of these points may be true. We've just covered as long as the pressure vessel is secure, but I think a lot of observers don't realise how many conditions as long as we can ascend depends on. To understand this, I'd like to briefly discuss an incident I was involved in. A few years ago, during a scuba dive, I had an uncontrolled ascent to surface. It was from 18 metres depth, so I was extremely unlikely to have suffered any serious injury, but I beat myself up over it for a long time afterwards. That is because I made a seemingly unrelated mistake that led to the incident. When buying my gear, I went with an expensive regulator, dry suit, and BCD, that's buoyancy control device. My thinking was that these elements were my direct life support, and I wanted to minimise the chance of them failing. While I was only qualified to dive shallow depths, I decided to cheap out on my fins. After all, they're just fins. I can't get hurt if they don't perform well, right? They'd just be an inconvenience. It turned out that on me, the fins were very slightly positively buoyant. They floated ever so slightly. It was irritating, but not a huge deal. I decided I'd get some better ones soon. In the meantime, I went on a training dive. During that dive, while my buddy was deploying a surface float, my cheap fin started pulling my feet up in the current. Not a huge deal. As I sort of struggled to get my feet back down, my buddy grabbed me to give me a hand. He accidentally grabbed my integrated weights, which is also another non-standard setup, by the way. My weights came out in his hand and I shot up to the surface. Both of us were fine due to a combination of good training and action from the rest of the team. Neither of us had any injuries whatsoever. But my non-safety critical fins, in inverted commas, non-safety critical fins, had directly caused a serious incident. The lesson here is that in a harsh environment, almost everything can become safety critical. There are a number of obvious examples on the Titan, but I want to focus on the most widely reported, the control system. First, let's look at the most direct aspect. The control unit is an off-the-shelf game controller. Even for the unmanned remote operated vehicles, ROVs, I used to work closely with, this would be completely out of the question. Some commentators have stated this is standard practice in the military. It is not. Game controllers are great for applications like drones, remote turrets, that kind of thing. I'm not aware of any example of them being used as a primary means of control or propulsion, especially for anything man-rated. I can reasonably imagine an off-the-shelf controller as a secondary that could be passed around passengers to let them have a go. Why not? That is providing you can mitigate some of the other concerns I'm about to talk about, which is more difficult than you may suspect. But as a primary means of control, absolutely not. The obvious points, such as Bluetooth connection, less reliable, can cause interference, are absolutely non-trivial here. It's easy to say, no, but control's non-life critical. We can ascend to the surface at any point. We have multiple redundancies for that. It's simply not true, especially for a wreck dive where a sudden loss of control could cause a collision. Even encountering difficulties during control of the vessel increases task loading on the operator, potentially creates a high-stress situation where mistakes are made. That's just the direct effects of a non-suitable control interface. Let's discuss some indirect effects. So I'll give oil platforms as an example. Everything that goes outside of the accommodation module must be fire rated. That means it's certified not to create sparks or fire. For an enclosed DSV, we'd expect similar, if not even more stringent requirements. Logitech game controllers most certainly do not have such a certification. Neither do lights from Camping World or LED power indicators from an electronics hobby store. And I doubt, and now admittedly this is speculation, the monitors and other electronics we see on the vessel are similarly rated. Electronics failing and giving off smoke may seem unlikely, but the stakes are so high, especially when they're used out of specification, as here, that the thought of riding a sealed vessel with any non-negligible risk of fire really does, and excuse the change of tone here, freak me out more than anything else I've discussed here. There are no person restraints. The occupants sat bare feet on the flat floor. This has two major issues. This opens up the possibility of disorientation for the pilot. It's a common issue in aviation. I'd expect him to have a fixed frame of reference relative to the rest of the craft, which is achieved by a decent seat and restraints. Secondly, general safety. Even a relatively trivial scenario of the craft surfacing in heavy sea would turn unpleasant at best with no restraints. At worst, it's not difficult to imagine occupants being seriously or fatally injured, particularly in an uncontrolled ascent or if the pilot loses the ability to steer the vessel. I'd also like to point out that the BBC documentary linked below recorded an incident in 2022 where the vessel reached the seabed only to realise one of the thrusters was installed backwards. And when I say reach the seabed, I mean the 4 kilometres down seabed at the Titanic. I'm not sure I really need to comment further on this, but I will say for an ROV that would be an instant abort and calmly return to surface. ROVs are expensive, but still remember they're still unmanned. They did not return to surface. They remapped the controls via text instructions from the surface and carried on. Now I will admit, they were only able to remap the controls because they were using a video game controller, so it is an unexpected benefit. But it's kind of a moot point when any rational engineer would have identified the problem before diving, perhaps during some control checks near the surface, and cut the dive short. For any programmers out there, they pushed their code into prod in the most high-risk way possible. For more info on non-certified ancillary equipment, I recommend looking up the Kaprun disaster, where a store-bought electronics heater caused a fatal fire in a train in a tunnel, leading to 155 deaths. The death of the diver Dave Shaw also shares similar aspects, but that is a particularly upsetting story. All the following points don't really fit into a category of their own. Some have been misreported, so I'd like to add some clarity. Any single one of these would be a project killer in my experience. Rushton stated he hired young designers rather than, and I quote, white guys in their 50s. He is actually a white guy in his 50s, by the way. This has been largely reported as, I don't want to say the word, woke hiring. In all likelihood, it's just cost cutting. White guys in their 50s, especially for specialised applications like this, do not come cheap, and they won't hesitate to point out your shortcomings or even whistleblow, which literally happened to Oceangate in 2018. Young engineers are an order of magnitude cheaper, and will often go the extra mile to achieve the end goal while being unaware of the risks. And that's not to disparage young engineers. I love the attitude of opening up the deep sea to a younger generation, but I don't honestly believe that was Stockton's intention here. The egress hatch was widely reported as being sealed and only openable from the outside, and this is absolutely true, but I've seen reports stating this is standard practice. It is not. Every other DSV I've been able to verify has a plug hatch openable from both sides. I can play devil's advocate though. There is one case where an openable hatch caused a near disaster. Apollo 1 is often quoted here, but I'd like to discuss a prior incident, Mercury Redstone 4, where the hatch was prematurely blown, leading to the loss of the craft and almost the loss of the pilot. In this case, an operator-enabled hatch actually increased the risk, and yes, I am aware of the controversy surrounding exactly what happened here, but the fact is the hatch blew off early. Now, as I am playing devil's advocate, I will say I have seen no evidence Oceangate took necessary mitigations to ensure an externally accessible hatch was actually safer, fire management, redundant breathing systems, etc. But it's always worth recognising that risks and the interplay between them are not always as glaringly obvious as we may think. By the way, Gus Grissom, who was the pilot for Mercury Redstone 4, was actually subsequently killed in the Apollo 1 fire, which was a cruel twist of fate. Challenger Deep did have an externally sealable hatch. It was an entirely different class of vessel, however. It was also built to industry standards and was independently certified. Here is an unmanned ROV. Here is the Alvin DSV. Oh, Alvin. I wish I could talk about Alvin instead. Here is Titan. There are external cables everywhere. In fact, here is a clip showing what appears to be zip ties holding them in place. One of the two easily foreseeable unrecoverable scenarios for the craft is entanglement, the other being loss of hull integrity. As with some of my other points, I don't really think I need to expand any further. From what I understand, those exposed thrusters were covered with cowlings for later dives. The vessel was still very much at risk of entanglement, but it may not have been as dramatic as I thought at the time. Let's be honest, they had many other issues to worry about. So I'm going to leave it here. There is much more I could say, and I've put some of my uncovered points on the screen, but I think I've communicated what I intended. It's alarming to see this Silicon Valley mantra of move fast and break things gradually creep into the real world, and even worse to see this philosophy imposed on participants without their knowledge. As a final thought, Stockton previously stated he was not pursuing rigorous testing and certification because, as I quote, most subsea accidents are caused by operator error. I leave to the viewer to theorise why, until now, subsea accidents due to mechanical failure have been so rare in recent years. Thank you.